So now we are going to look into how to design a tunable capacitors with an objective to use it in a oscillator circuit to design a voltage controlled oscillator. The simplest way to obtain a tunable capacitor on chip is by using a reverse biased PN junction. So we know that if a PN junction diode is reverse biased, some voltage, say some VT, then the equivalent circuit looks like a capacitor due to the depletion region. So this junction capacitance is a function of reverse biased voltage, and by controlling this VD we can control the CJ. Reverse biased voltage, this is junction cap. And this relationship approximately can be shown as CJ to be equal to CJ naught divided by 1 plus VD by V naught with some exponent M. So this CJ naught is the capacitance when VD is 0, and when we start increasing the VD, this is reverse biasing, then the junction cap keeps on decreasing because depletion region starts widening. And V naught here is the built-in potential of the PN junction, and we know that this built-in potential for PN junction in silicon is around 0.7, 0.8, and for the PN junction diodes which can be realized on chip, this factor M is also small, somewhere around 0.3. So overall the amount of tunability which we can get using this reverse biased PN junction is very limited. Limited cap tuning using integrated PN junction diode. This is the VT. And show that this CJ is tunable by VT. Since we know that in a CMOS process we have access to MOSFETs, and we also know that the MOSFETs have their effective gate source capacitance, which is a function of the gate voltage. So generally in a CMOS process we tend to use a MOS-based variable capacitor. MOS-based variable cap. So we know that if we take a MOSFET, in this case let's take an NMOS. This is the VGS, and let us try to find the capacitance CMOS. Then we know that capacitance of this MOSFET will be a function of VGS, and when the VGS is high, then the MOSFET, in this case this NMOS, is going to be having an inverted channel. So this channel will make sure the looking in capacitance is close to the oxide capacitance. So this capacitance of this MOSFET will be close to the oxide capacitance. But as we start reducing VGS, then the MOSFET starts entering into the weak inversion region, and because of the depletion region formed, the effective capacitance gets reduced. But if we keep on reducing VGS and make this VGS negative, then we see that the capacitance again increases and it starts touching this COX value. So here again this capacitance increases because of accumulation. So now instead of having electrons in the channel, in the accumulation region, we are going to have holes. So holes are going to make the region between the source drain to be highly conductive, so that the effective capacitance is only the oxide capacitance. So here we are in strong inversion. Here we are in accumulation. Now we can see that we can get this kind of voltage dependent capacitance using a MOSFET. This capacitance versus voltage characteristics is not monotonic. So first it is, so if you start from the high VGS value, it is going to reduce with VGS. But again, it is increasing. And many times in our application, we will see that because of the large swing present at the output of the oscillator, the VGS can also become negative. So as a result of which, we are going to get a non-monotonic CV characteristics using a regular MOSFET, which is not desirable, especially when we are using a VCO in some kind of a feedback system where we are trying to set a specific frequency by controlling the VGS. This kind of non-monotonic behavior can make such feedback systems unstable. We get a non-monotonic tunable cap using MOSFET. This part is not desirable in a feedback system. So it has been found that instead of using a standard MOSFET to realize a variable cap, we can do some modification in the MOSFET structure. For example, we can fabricate the NMOS structure inside an anvil itself, and such a structure is going to give you a monotonic capacitance voltage characteristics. So if we realize the same NMOS structure, you've got this gate oxide, some gate metallization. These are the N plus diffusion regions. But instead of using a P substrate, if we place this structure inside an anvil, now if we take this connection out, this is the gate. Call this as S. Now see that this is not a regular NMOS, but here we have put the same NMOS structure within an anvil. Now, such a structure, you can see that when we apply a high gate voltage, it is going to pull a lot of electrons towards the channel. So this channel is going to be heavily accumulated. Whereas when we reduce this VGS, then the charge concentration is going to reduce and we are going to get a lower capacitance. So such a structure will only go between accumulation and depletion. There is no inversion. So as a result of which, the overall capacitance versus voltage characteristics is also going to be monotonic. This is also called as MOS-based varactor, and if we look at the CV behavior, then the capacitance between these two terminals, say CGS, VGS, is again going to be close to the oxide capacitance for high value of VGS, where it is going to reduce with VGS in a monotonic manner. So here it is in accumulation. As a monotonic CV relationship. So these structures where there we can obtain a variable capacitor is also called as varactor. And these MOS-based varactors are really popular because of their high tuning ratio. So you can change the capacitance between high value to low value as well as their monotonic CV relationship. So these kind of MOS-based varactors are really popular in CMOS process. Varactor application. So we are also going to use these kind of varactors for the VCO design.